Next thing I want to look at, magnetically shielded rooms. And there's different types of magnetically shielded rooms. If you want to shield high frequencies, you can make them out of copper, aluminum, and if you want to shield lower frequency fields, incorporate some mumetal. Now, the more mumetal you have in a magnetically shielded room, the more expensive it's going to be. Okay. So we can go ahead and simulate a magnetically shielded room. First, we'll look at a regular conducting type of magnetically shielded room. This is an AC magnetics problem. Let's look at the geometry. This is axial symmetry. And I have the magnetically shielded room that has roughly a 2-meter radius, and it's about, actually pretty small, I suppose. That would be about 2 meters tall. So you'd have to stoop over a little bit to stand inside of this. This is the air region, and this is the copper region. Now, it's hard to see the copper region on this scale, and it's a very fine mesh because we have a very thin copper shield. Okay. It's ½ centimeter thick. And let's look at the solution. Okay. So we're looking at the flux lines here at 0 degrees. Also, we can look at the current that's induced inside of the shield here. If we get closer here, we can see the current flow. This would be the eddy current flowing inside of the shield. We can animate the solution for different phases. Turn off the animation, and we can look at a contour plot along the center. And once again, this is a 50 Hertz field. And we can calculate the shielding factor versus frequency using LabelMover as we did for the simple sphere we started off with. However, they'll take a little bit longer because this has a lot more nodes to it. So I'm going to look at a radial contour roughly along the center of the shield. And we can look at the XY plot. Okay. And this is, look at the flux density here. It gets larger towards the edge of the wall, and roughly nanotesla inside of the shield here. Okay. We can get our individual tool, sample points inside to get an idea of where the shielding is. This roughly nanotesla here, and outside we have about 300 nanotesla. Okay. Which would be a typical type of power line signal, 50 or 60 Hertz. Okay. So it looks like getting a couple orders of magnitude shielding. Now, we can add additional layers to our magnetic shield, our magnetically shielded room. And I'm going to add an extra layer of mumetal as well as another copper layer. The easiest way to do that is to use your, insert your rectangle here, giving your dimensions of the magnetic shield and just increasing it slightly, and put in subsequent rectangles, and you can do that. Okay, this is our layered shield. And this is the same, roughly the same geometry we had previously. Except now we have 3 layers. Let's zoom in and see. Okay. There they are. So if we look at our block labels, this is the air region. This is the copper region. And this is mumetal. Okay. These are all half centimeter thickness. The air gaps are half a centimeter, and each layer is half a centimeter. This would probably be a pretty expensive shield. Probably about $1 million. Let's go ahead and look at the solution. Okay. And we can compare the shielding factors. Outside here, it's roughly 300 nanotesla at 50 hertz. And you can see inside here it's much, much bigger, much, much smaller. 10 to the negative 13 Tesla. That's about 100 femtotesla, which is good enough for cardiomagnetism. If we're going to do neuromagnetic measurements, we really need to be down into the femtotesla range, which is approaching the squid sensitivity. Okay. Let's go ahead and solve it. To get an idea of the solution time here. This is a relatively slow laptop. It's a 2005 Toshiba. Sorry to waste a minute here. This will probably go like 5 times faster on a more modern machine. Okay. I want to calculate the total number of nodes in this particular model. Okay, so this is about 178,000 nodes. We're probably using more than we actually need for this particular problem. Next, I'd like to look at a magnetically shielded room with openings. We previously looked at a closed magnetically shielded room. And this time I'm going to be using some symmetry in the problem to reduce our computation time. So this is an AC magnetics problem. The geometry of the problem, we have similar to the previous geometry, except now I'm making use of the fact that we have zero tangential field along the symmetry axis. So this is our multi-layered magnetically shielded room that consists of two copper layers surrounding a mumetal layer, and this is the actual solution here where you can see that there's zero tangential magnetic field. And if we look at the corner region, you can see that the central layer, the magnetically, the mumetal region, is screening the magnetic fields, and we have the two copper layers surrounding it there. So now what I'd like to do is put a port in here that might simulate a door or an opening. So I'm going to create a 1 millimeter gap in this region here. So, and then we can compare the shielding with and without the gap in the center of the shield here. Okay, so let me close this problem. Okay, here's once again the geometry file. And now I want to look at the region where we have the gap. Okay, so if we look at the block labels, this is the air region, and then we have the copper layers, and then the surrounding mumetal layers. So there's going to be a tiny gap here, you can see, between the side wall, the cylindrical portion, and the flat region here. And this is going to affect our shielding factor slightly. So if we want to look at our shielding factor, we can pick a test point inside the model. And I picked the very central part of the shield here to look at the screen field. So in order to do this, I'm going to use the parametric analysis with LabelMover. Okay. And our base problem is given by this model file. And we want to add values. And this is our test point where we want to look at the flux density at the point at the center of the shield. So I'm looking at this test point here. Okay. And now let's record steps. So I'm changing the problem properties here. I'm changing the frequency, which is currently 1 hertz, and I'm going to change it 100%. We'll add a step. And I'm going to repeat the step a couple times. Okay, we'll do one more. Okay. We'll get the results. Okay, so the initial flux density is about 1.4 nanotesla for the first problem. we have 3 times 10 to the negative 10 Tesla for 2 hertz. So we have roughly a factor of 3 reduction in the field as we go from 1 to 2 hertz. So this is going to be the pattern. We're continuing to have greater shielding at higher frequencies. Now the mumetal is great for shielding at low frequencies. We have a central layer of mumetal, and the outer conductors are going to assist in shielding at higher frequencies. So we're just modeling a few points here, and then I'll show you the result of more broader frequency range. So we're continuing to attenuate the external noise field, roughly 10 picotesla at this point. Two picotesla, 16 hertz. Okay, so we can look at a plot of the shielding as a function of frequency here, and you can see as we're increasing the frequency that the magnetic field is progressively more well shielded. So the shield's less efficient for low frequency fields. Now, I want to look at a broader frequency range and also compare the shield with and without the gap here. So this shows the shielding factor, which is the ratio of the magnetic field outside to the interior magnetic field at the test point. And we are sweeping the frequency in a range up to from 1 to about 50 kilohertz in this particular simulation. So the upper graph shows the shielding factor with the gap, and so we have greater attenuation, obviously, with no gap here, but with the 1 millimeter gap is not causing a very significant difference in the shielding factor here.